After seeing a couple of examples of how not to undo some of our derivative rules, we next want to think about how to undo one of our rules, and we're going to be looking at undoing the chain rule in this section. This turns out to actually be the easiest derivative rule to undo, even though it's maybe one of the trickiest derivative rules to apply, but this is what we're going to focus on in this section. So example 4, we're asked to find an antiderivative of cosine of pi t. And maybe we want to remember that what we did in the previous section, or in the previous video, was we looked at undoing each of the individual pieces. So we said, well, let's antiderive cosine and get sine. Let's antiderive pi t and get pi t squared over 2. And that didn't work out so well for us. But maybe we can get a little glimpse of what's going on here by thinking about what did go well in this process and how can we change what didn't go well so that we end up with the right antiderivative. So when we were going through this process, we were hoping to get a function whose derivative is cosine of pi t. We got a function whose derivative was kind of close, but maybe not that close. Some issues that we ran into here were this extra kind of pi t floating around outside of the function, and we also had this pi t squared over 2 inside the cosine. That wasn't so great. But something that went well for us was, well, we at least got this cosine. Great. And we got this cosine because the chain rule says take the derivative of the outside function and leave the inside stuff there. So if we're hoping to get a cosine of pi t out, maybe our original function, the function that we're starting with, that we want to take the derivative of, should have a sine on the outside, but it should have a pi t on the inside of the sine. That way, when we take the derivative of sine of pi t, the cosine will be there, as will the pi t on the inside. So let's give that a try. We certainly have the method of guess and check available to us when finding these antiderivatives. So let's take a guess that an antiderivative is sine of pi t. So if this is our guess, and now we want to go through the check procedure of this, the derivative, so d dt of sine of pi t, our chain rule says derivative of the outside times derivative of the inside, so I'm using pi t as my inside function here, and sine as my outside function. So derivative of the outside, derivative of sine, is cosine. We're going to leave the inside function alone, pi t. And now we multiply by the derivative of the inside function. So the derivative of pi t we know to be pi. And we're closer. This answer certainly looks a lot more like cosine of pi t than the previous answer did, but we're not quite there yet. We have this extra pi floating around on the outside. And the way that we're going to remedy that is with a new guess. We're going to guess 1 over pi times the sine of pi t. We know that pi is going to pop out at the end because of the chain rule, so we're going to anticipate that and counteract it by putting a 1 over pi out front of the function. This isn't going to create too many more problems with new derivative rules popping up, because derivatives preserve constant multiples. So when we're taking the derivative, that 1 over pi is going to stick around all the way until the end. So let's go ahead and verify that this works. So we have the derivative of 1 over pi times sine of pi t. We know the 1 over pi can come out front of the derivative, so we have 1 over t times d dt of sine of pi t. And we just went through how to take the derivative of sine of pi t. It is cosine of pi t times pi. And now we see that the 2 pi's that I have here cancel out, and so I'm left with cosine of pi t. This is exactly what we wanted. So we have that an antiderivative is 1 over pi sine of pi t. Certainly not the only one. We could have added 5 to this. We could have added 1,000,000 to this. We could have added negative 100 to this. But this is an antiderivative of cosine of pi t. And so we have at least initially figured out how to undo the chain rule. Notice that kind of the key piece here was that we identified this inside function and we left it alone. So that's going to be one of the important procedures when we're doing this process of undoing the chain rule. So let's think maybe about how we might do this more generally. In order to do that, we should probably state what the chain rule says. So recall that the chain rule says that the derivative of some function with respect to x is the derivative of that function with respect to u times the derivative of u with respect to x. Frequently, when we are doing antiderivatives, we're given a function and we want to find the f whose derivative is the function that we're given. So this left-hand side here, this df dx, is frequently the thing that we are given. We want to find f. So the way that we're going to do that is we're going to try to recognize the thing that we're given as the right-hand side. So in other words, we want to find a u so that the given thing, so that the given function looks like the derivative of f with respect to u times the derivative of u with respect to x. So we want to find a u so that the given function looks like the right-hand side here. How we did that with the previous example was we were given this function cosine of pi t. We found a u, this being the inside function for our chain rule. So we said that was u equals pi t. And we recognized this as, we recognized this cosine of pi t as the derivative of, so if we're thinking about u equal to pi t here, we recognized this as the derivative ddu of sine of u, of 1 over pi sine of u, times du dt. This du dt here was the pi that we had, and this 1 over pi sine u, that was the 1 over pi times cosine of pi t component. So we kind of created this u in order to make these things cancel out. Let's go ahead and see another example in order to clarify some of this concept. So here we want to compute the integral of 2x e to the x squared dx. So step 1, we want to identify a u. So that 2x e to the x squared equals df du, the derivative of something with respect to u, times the derivative of u with respect to x. So here I'm going to notice that I have a couple of different pieces. One of those pieces is this x squared here. Another of those pieces is this 2x. And the relationship that I want to notice here is that 2x is the derivative of x squared. In other words, if I let u equal x squared, this is my du dx, and this x squared here is my u. So this looks good because I've got a du dx here and I've got a times du dx here, and hopefully I can recognize this as the derivative of something with respect to u. So let's go ahead and make those substitutions. So here, if I let u be x squared, then I recognize that 2x e to the x squared is du dx, that accounts for my 2x, times e to the u. And now what I want to do is I want to think about, well, what is e to the u the derivative of? Well, e to the u is the derivative of e to the u. So if I let f equal e to the u, I now recognize that this thing here is du dx times df du, which I know is the same thing as df dx. In other words, this function that we've started with, 2x e to the x squared, is the derivative with respect to x of this function f, which is e to the u. But it's not we want to think about f in terms of x squared. So we'll think about this, u being x squared means that f of x is the function e to the x squared. Maybe we want to go back and check. So here we have our function f of x equals e to the x squared. And in order to to see if this is an antiderivative, we're going to take its derivative. So f prime of x here, again I have a chain rule, this being the inside function being x squared, the outside function being e to the stuff. We know that the derivative of e to the stuff is e to the stuff. And then we multiply by the derivative of that inside function. So in this case, the derivative of x squared is 2x. So yes, we have found an antiderivative, and that allows us to conclude that the general integral here, conclude that the integral of e to the x squared times 2x dx is equal to e to the x squared plus c. All right, so this was kind of a confusing process, and it certainly doesn't look like a nice algorithm that we can do in order to actually do future problems. It kind of was a little bit messy. We had to deal with a little bit of luck in kind of getting some things to work out nicely in these steps, and so we want a slightly better way of actually doing this problem. So let's think about an alternate method. I have this function, I have this integral here of 2x e to the x squared dx, and I had this substitution u equals x squared going on. So maybe what I want to do is rewrite this integral in terms of u. So I have 2x e to the u dx, and this looks maybe even worse than when we started. We have a couple of problems here. Namely, we have two variables going on. We have x's and we have u's. So in order to remedy this, maybe the thing that I'm going to think that's hardest to get rid of is this dx here. We want to think about what is dx in terms of u. And here's where we can really take advantage of Leibniz's notation for derivatives. The fact that Leibniz wrote his derivatives as these things that look like fractions but aren't is really going to be beneficial in this u substitution process for us, because we're going to be able to pretend for a time that they are fractions. I know that du dx, because u is x squared, du dx is 2x, and we can pretend that this implies that du equals 2x dx. So this is not really a meaningful statement in terms of mathematics. We don't really know. Du doesn't mean anything on its own. Dx doesn't mean anything on its own. But it sure looks like it does. And it sure looks like what we can do is we can take this 2x dx that's in this integral here, and because 2x dx equals du, we can make that substitution. In other words, I'm going to replace 2x dx by du. So I'm left with e to the u. I'm getting rid of 2x dx, and I'm writing it as du. And now we have an integral that has one variable in it. It only has u, and this is a really easy integral for us to do. This is a much simpler function. We know that the integral of e to the u is e to the u plus c. And now we can go back and we can substitute x squared in for u. So this substitution process here, where we picked a u and we figured out, we turned this integral that we started with into a simpler integral in terms of only u's, there were no x's involved here, really allowed us to simplify this integration procedure and write kind of this undoing of the chain rule in a nice way. So you'll frequently hear this process called u substitution because we often use the letter u, though we certainly don't have to. And this is going to be our general method for undoing the chain